So first, I'd like to thank the organizers for the very kind invitation to come here and give a talk. It's also a real pleasure to actually follow from Daniel's talk, because you're going to see that we cover two different sections that's actually very similar. So here I'll talk first about thermalization, again, but it's actually a form of Krylov-restricted thermalization. And in the second half of my talk, I'll also mention lattice gauge theory. And so this work is actually done in collaboration with our chair and organizer, Wen Wei, and also a collaborator, a colleague at Duke, Natalie Klo. So even though we'll talk about thermalization and lattice gauge theory, we're going to see it from a very different perspective today, now focusing on some interesting manifestations of the Hilbert space being fractured into exponentially many disjointed subspaces, also known as Hilbert space fragmentation. And in our experiment, and I'll talk about this from an experimentalist point of view, I'm an experimentalist, we work with Rydberg atom arrays, which Daniel also mentioned briefly. Okay, so in general, when you've got a system that's non-integrable and you bring it out of equilibrium, it's going to thermalize. And this thermalization has so far been observed to be consistent with the eigenstate thermalization hypothesis. Right? There's been many beautiful works done on this. And just to state briefly, in the ETH, where you have an isolated quantum system that you prepare in a pure state, right? It's quenched. Over time, as it evolves and you make local measurements, it's going to be rendered indistinguishable compared to if you had sampled from a thermal ensemble of states. And this is not just any thermal ensemble, it's states that lie within a narrow energy window. And this is actually an important point that I'll come back to later on in the middle of my talk. Okay, you've got counterexamples to the eigenstate thermalization hypothesis, and those are usually associated with memory, right? One of them, famous examples being many-body localization, where you've got some out-of-equilibrium state and it stays in that state over time. And then you also have quantum many-body scars. Again, some initial state. Now you do allow it to evolve, but then you get these persistent oscillations coming back to the same initial state that you have. And you can see them over here in a theoretical calculation as sort of these tower of scar states over here. Okay, so where you have scarring and many-body localization, those phenomena associated with memory is usually considered to be diametrically opposed to thermalization. And so the question we want to ask is there a phenomenon that you can observe where somehow thermalization and memory can actually occur at the same time? It sounds a bit weird, very counterintuitive, but if you can actually access such a regime, that could be quite interesting, because where thermalization is usually associated with this rapid propagation of entanglement, and conversely memory is this entanglement freezing, maybe if you can have this intermediate regime, that might lead to new ways to control entanglement propagation. Now, I don't actually talk about any control of this entanglement propagation in my talk, but I want to pose this question out to sort of stimulate discussions, and maybe some of you who work on quantum control might have some interesting suggestions on it. Okay, so coming back to how you can get thermalization and memory to co-occur, one hint in which this can occur is looking at fragmented systems. And again, these are systems where the Hilbert space has been fractured into exponentially many disjointed fragments, also known as Krylov subspaces. I want to make a distinction between this Hilbert space fragmentation and what we usually know of as symmetry sectors. Okay, where you've got symmetry sectors, that's really chopping up your Hilbert space into polynomially many disjointed subspaces. Okay, but this is actually an exponential with the array size or the system size that I'm talking about. And this sort of exponential fracturing that you have can sometimes even occur within a given symmetry sector. Okay? So these fragmented systems are generally quite interesting for studying a host of exotic phenomena like fractal dynamics, the TJZ model, the fractional quantum Hall effect. And one of the things that, interesting phenomena that has been predicted by Mutgauya and co-authors is that you can start actually with an initial state in a given Krylov subspace. And when you allow it to thermalize, now the entanglement is constrained to only spread within this given Krylov subspace. Okay, so this is known as Krylov-restricted thermalization. So if you look at it, you should get actual thermalization that's happening within the Krylov subspace, but somehow you can still preserve some memory or some characteristics of the initial state by identifying which Krylov subspace in which this thermalization had occurred. Okay, in general, if you want to effect these fragmented models, you want to impose kinetic constraints. And actually, a lot of the pioneering work on sort of experimentally realizing these fragmented systems was done in Munich in the group of Emanuel Bloch and Monika Eidelsberger with initially 1D fermions in a tilted optical lattice. And basically, you have this hopping, tunneling that's allowed between sort of the different sites, but the hopping occurs in a way that actually conserves the center of mass. Right? And I believe Emanuel will mention some of this beautiful work as well tomorrow in his talk. So besides 1D fermions, there's also 1D bosons, both in Munich and also in the Takahashi group. Recently, this was extended now to a 2-dimensional system, which is very exciting, where they were able to observe fractons, also in Munich. Rydberg atom arrays, of course, people have worked with them for quite a while now, but its connections to Hilbert space fragmentation was maybe explored more actively only more recently, and I'll have another slide later that focuses more on this. And then now also, just this year, there was work appearing in terms of using superconducting qubits to study the dynamics that's associated with this Hilbert space fragmentation. Okay, so these are a few interesting experimental realizations. So as mentioned, in my lab, we work with Rydberg atom arrays, and these are nice because you've got single atoms that you trap in optical tweezers, that you can move these atoms around, and you can generate many of these tweezers, many of these qubits, and the record right now is in the Andres group at Caltech, where you can have 6,100 of these qubits that you can control coherently. So that's very impressive. There are many things that you can program with these neutral atom arrays, right? You can arrange them in all sorts of different geometries. So here I show a few pictures from my laboratory with the Kagome honeycomb Sierpinski triangle. You can see a lot of these geometries are very inspired by condensed matter physics problems. And because you want to use these atom arrays for quantum simulation, it's important to start off with defect-free arrays to begin with. Otherwise, it's not very meaningful to be able to write down a Hamiltonian if you've got defects. And so here we show in our lab just a couple of years ago that we can rearrange atoms where we can get defect-free arrays with up to 225 single atoms. And we can do this fast enough such that you can concatenate these rearrangement cycles and eventually get maybe about 1 in 3 shots having this more than 200 atom array. Of course, today this is not a very large number by comparison, but it's still quite interesting to realize what we can see. Okay, unfortunately, in this talk, I'm now going to deflate all your expectations and bring you down to 1D. Even though we were able to create these geometries, there were a few other logistical constraints that prevented us from working with a full 2D array. And so in this work, we work with 1D chains of about 15 to 20 atoms or so, and we concatenate them just to get statistics. Okay, so these are 3 defect-free single-shot images of these atom arrays. Okay, the Hamiltonian that we use, this was also recently presented in the last talk, is sort of this Rydberg Hamiltonian, which you can map onto the Ising model, where this is kind of like your transverse magnetic field, your longitudinal magnetic field. And this is the van der Waals interaction between 2 atoms that occur only when they're both in the Rydberg state. And that goes as sort of a 1 to the R6 with the distance between the atoms, which we can control precisely. And for this analog quantum simulation that I will talk about, we work with the qubit states being the ground state and the Rydberg state. Usually you see this Ising model being written in such a form, and here I'm going to suggestively rewrite the projector onto the Rydberg state in terms of the Q projector, and you'll see why in a few slides. Okay, so coming back to Hilbert space fragmentation, we want fragmented models, which means we want to impose kinetic constraints. One popular way to impose kinetic constraints is through the Rydberg blockade, right? Which means that where you've got 2 atoms that are close to each other, well within the Rydberg blockade radius, you cannot simultaneously excite them both to the Rydberg state. And that's forbidden by energy. In our lab, actually, a couple of years ago, we found some ways to get around this issue, where we can also actually have 2 atoms undergo Rydberg blockade, even though they are a little bit outside of the static Rydberg blockade radius, and we can actually show entanglement. I won't talk about this here, but feel free to ask me about it later on during coffee or lunch. And then where we can now tune this Rydberg blockade radius to encompass sort of the spacing between the nearest neighbors, we can realize what is called a PXP model, which means that this atom in the middle can only flip its spin from, say, the ground state to the Rydberg state and vice versa, only if it is surrounded by 2 ground state atoms. Okay, that is the PXP Hamiltonian, where P refers to the ground state projector. Besides this Rydberg blockade, which is usually realized sort of close to resonance, usually you can also have Rydberg spin exchange, where now you sort of dress the atoms far off resonantly, but you make that detuning resonant with the spin exchange interaction between two atoms. So you can actually have these dynamics where you conserve the number of Rydberg excitations, and a lot of that work was done in the group of Joaquin. What we like to work with in our lab is facilitation, which is also known as Rydberg anti-blockade. Okay, so when you have two atoms that are close to each other, it is actually possible to excite them both to the Rydberg state, but all you have to do is just compensate for this van der Waals interaction strength between them, right? Previously, where they were off resonance, just compensate for that, and boom, you can bring them both to the Rydberg state. Now, this is very sensitive, of course, to the position of the two atoms, so this doesn't occur anywhere within the blockade sphere. It's only at a particular shell radius. Okay, so let's call that the facilitation shell, and if this atom lies over here, yes, you can excite that to the Rydberg state. Okay, that's the physics for two atoms. If you've got three atoms and you arrange them in a chain, then I can simply change this atom from the ground state to the Rydberg state if I compensate for sort of the van der Waals interaction contribution from the left and the right. Okay, so just 2 times V over here. Now you can see how we can extend this to an entire chain, right? And we can realize what is sort of called the QXQ model, where Q is the Rydberg state projector, which is simply dual to the PXP model. Okay, all we have to do is just change the detuning now to compensate for this facilitation shell. So now this atom in the middle has to sit at the facilitation shell radius of the Rydberg atom to the left and to the right, then it's able to flip its spin. So just like how in the PXP model, you were able to see Z2 quantum antibody scars, you can also see actually the same scarring behavior in the QXQ model. But now, immediately, you can see something actually different between the two. Okay, so we start off with a new state that is somewhere in the bulk, but then we are surrounded by ground state atoms on the ends. And in the QXQ model, those are frozen dynamics, right? Whereas you actually see sort of this, this new state sort of extending out in the PXP model. Why is that so? Okay, it's very simple. It's simply because in the QXQ model, where you've got these ground state atoms on the boundaries, you're never ever going to satisfy these QXQ projectors. So there's simply no dynamics over there. Okay, it's frozen. If you wanted to realize the same frozen dynamics in the PXP model, what do you need to do? Well, the two models are dual to each other, so I need to swap the ground state with the Rydberg state. So I need to have basically all these Rydberg atoms that are concatenated along the chain on the ends in order to see any frozen dynamics. But now immediately we run into a catch-22, right? You know that it's actually non-trivial to it's impossible, in fact, to actually have all these Rydberg atoms in a chain, precisely because you had needed this Rydberg blockade to occur in order to realize the PXP model. Okay, whereas in the QXQ it's actually trivial. So this starts to tell you that there's something interesting going on with the facilitation. Okay, in our group, we're a little bit ambitious, so we want to go actually to beyond nearest neighbors, to sort of next nearest neighbor atoms. And now we place this atom at the facilitation shell radius of the next nearest neighbor over here. And we've also extended the blockade radius. Okay, so now we have a very strongly constrained system where this atom in the middle can only flip its spin when it's surrounded by 2 ground state projectors and 2 other next nearest neighbors that are both in the Rydberg state. So it's a QPXPQ model. And what you can now see actually is Z4 scarring. Okay, so you can start off with a Z4 ordered state initially, so 1 Rydberg atom every 4 atoms. And after some time, you can come back sort of to the same initial state. Okay, and if you sort of partition your array into 2 different subarrays and do the Fourier transform on the dynamics in one of the 2 subarrays, you can see this Fourier peak, which is where your oscillations are going on for your scars. Whereas in the other subarray, you're pretty much always frozen in the ground state. Okay, this is interesting, and in fact, we can go further, right? By combining blockade and facilitation, and also going to even larger and larger extents, we can really realize a whole class of these strongly constrained models, QPPX, PPQ, that doesn't sound very fun to read, but you can realize these Z6 scars now. So in one of the 3 subarrays, you can have this Fourier peak, and then in the other 2 subarrays, it's frozen in the ground state. Okay, but I had digressed a little bit. I want to talk about the Hilbert space structure, right? So what does the Hilbert space structure look like for this kind of, say, QPXPQ model as an example? What you're looking at here is sort of the Hamiltonian, right? And each black dot is a non-zero matrix element between the different product states that we have written down over here. And everything within this sort of first red block is what we call the PXP subspace, where there's no Rydberg blockade violations, okay, only single Rydberg atoms everywhere. And we can see actually there's a nice block diagonal structure, which we had understood previously in terms of, well, if you've got only single Rydberg atoms here, Rydberg pairs, and so on, they are all separated by energy. And now we separate that more finely, right, the fine structure of that in terms of also V1, the next nearest neighbor. But now, we don't only want to care about sorting in terms of energy, but we also want to track where the Rydberg excitations actually lie. So if we follow where the Rydberg excitations are, and we see that they're on the even sites, we'll just say that they belong to, say, an even configurational subspace. Okay, the odd sites in the odd configurational subspace. The mixed one actually with a more fine-grained way of tracking where the Rydberg configurations are, depending on basically where the domain walls are. But for now, for pedagogical reasons, let's just call them the mixed subspace. Already, you can see that when you now rearrange the product states basis according to both energy and spatial configuration, you can see that these are 2 degrees of freedom that can both sort of fragment your Hilbert space. Okay, so I promised to talk about Krylov restricted thermalization, and so far we have almost all the ingredients that we need to see that. To see thermalization, now we need to selectively relax some kinetic constraints, and we do that by simply adding a second detuning, okay? And this allows us to now release some of these kinetic constraints, but interestingly, even with the second detuning, with this 2-drive Hamiltonian, there's actually no coupling between, say, atoms in states in the odd subspace versus those in the even subspace at all. Okay, so this actually is a way for us to see this Krylov restricted thermalization. And now we can look at what the experiment tells us. Okay, previously in the QPXPQ model, where we actually saw this scarring behavior going on in one of the subarrays, now you actually see a rapid thermalization, a rapid decay of this staggered magnetization towards sort of the thermal prediction value. Of course, we don't only measure just the overall magnetization, we have single-site resolution, so you can actually look at also the microstate projections of these experimentally measured bit strings. And previously, where we saw the Z4 scars, you can see these oscillations if you squint, okay? And these scars were also observed previously in the PXP model in the Harvard-MIT collaboration. Now, where you have the 2-drive model that's going on that selectively releases those constraints, you see a much more uniform covering, actually, of these microstate projections. This experiment, we also back it up by theory and seeing that actually the entanglement entropy rises up to a thermal value much more rapidly when you've got this 2-drive model, and also the entanglement entropy curve is now a lot smoother as a function of energy. Okay, of course, now if you want to look at a smoking gun signature of seeing Krylov restricted thermalization, what you want to see is that where you've prepared 2 different initial states that have the same energy to all orders, exact same energy, you should see that actually they thermalize to very different patterns. And that is indeed what we see in this particular case. So in one case, you can get the freezing of the atoms in the ground state only on sort of the even sites and vice versa. And if you look at sort of the long time behavior, now you get good overlap between the ground state probabilities that's measured versus what you expect from applying the eigenstate thermalization hypothesis to that particular configurational subspace. Okay, so in other words, in short, the eigenstate thermalization hypothesis does work very, very well when you only consider a particular Krylov subspace, but this is a very strong violation of the eigenstate thermalization hypothesis with respect to the full Hilbert space, right? Because even though they've got the same energy, they never thermalize with each other. Okay, so far I've talked about how there exist different Hilbert space fragments. And then the question now I want to ask is, now what happens when we consider the size of these Hilbert space fragments? So in other words, what happens when the size of your largest Hilbert space becomes a vanishing fraction of the entire Hilbert space? Okay, this is a regime known as strong fragmentation. So what happens when you've got very strong fragmentation going on? Turns out that you can have some subtle effects of localization. Okay, instead of subtle aspects of thermalization, you have a subtle aspect of localization. To appreciate that, let's take a look at conventional many-body localization. And actually, this also includes Stark MBL. So in many-body localization, it's phenomenologically understood to be described by these conserved operators with quasi-local support. Okay, in other words, these localized integrals of motion. And in general, if you've got these non-local conservation laws, those are not expected to impede thermalization. But interestingly, when you've got Hilbert space fragmentation going on, right, these conserved operators that are non-local are actually the labels for different Krylov subspaces. So the question we want to ask is that, does this mean that you only expect to see thermalization and not localization? Well, it turns out that in the limit of this strong fragmentation, you can actually get a subtle form of localization, and this is known as statistical localization. Okay? So in other words, when you take actually the expectation values of these conserved operators, what you actually get is now you pick up a vanishing contribution from the entire system, and therefore they actually appear local, just because that contribution is so small. And this only shows up when you're taking a statistical average, so it's an expectation value. And this was first put forth actually by Rakowski and co-authors about 5 years ago, and they had investigated these for two models, the TJZ model and this spin 1-3 side model. And they had derived analytical solutions for these statistically localized integrals of motion. Right? These conserved operators that they found to be statistically localized. And in our case, actually, what we did now is to experimentally reconstruct these as Lioms. And we actually do this in a new model, which I will discuss, associated with the Rydberg atom arrays. And importantly, we also do this in a place where now these conservation laws actually hold some physical significance, which is using the Rydberg atom arrays as a lattice gauge theory quantum simulator. Okay, so lattice gauge theories, they really form an interesting basic framework for describing many aspects of physics, from standard model to others. There's been a lot of interest now in quantum simulation with these lattice gauge theories, and a lot of work pioneered by Federica's seminal paper on how you can map these Rydberg atom arrays onto a U1 lattice gauge theory. Daniel had already gone through this mapping in his talk, and so I'll go through the next bit a little bit faster. But briefly, to see this mapping, you have the ground and the Rydberg states that you can map onto electric field strings that's pointing to the left or to the right. So if they reside on the odd bonds, for instance, the ground states, they point to the right, and then that staggered mapping holds for those atoms on the even bonds. Now you can inflate basically these electric strings with charges that, in a way that obeys Gauss's law. So now you can see that you form these electric charge clusters, okay, over here, and those charge clusters are separated by sort of at least two vacua that you can see. Okay, so that's just a mapping from the Rydberg atom array to the U1 lattice gauge theory. And the model that we now work with is with a single detuning, and this detuning is such that it compensates for the next nearest neighbor van der Waals interaction strength. Okay, so delta equals to V1. What this is known as is also the PPXPQ plus QPXPP model. So you can see how this works, right? So for instance, if you've got this part of the Rydberg chain that satisfies the Q projector, the P and projectors and so on, then you can actually flip the spin of this atom in the middle. Okay, you can change that from a ground state to the Rydberg state. And when you've done so, what you've effectively done in this language of sort of the electric strings and charges is that you shrunk the size of this electric charge cluster over here. Okay, and then for this spin flip behavior to be well defined at the boundaries, we inflate sort of the boundaries with these virtual ground state atoms, okay, over here. And over time, what you can see is that these electric charge clusters can actually shrink and grow. Okay, but then because you're always changing them by sort of one pair of vacua or one pair of charges at a time, they have to conserve both the number of electric charge clusters and also the net charge pattern. Okay, and so this gives us actually a very nice physical understanding for where Hilbert space fragmentation comes from, right? Where you have satisfied sort of this Rydberg blockade constraint, you're in the PXP Hamiltonian subspace, then you have satisfied Gauss's law. And then within that, right, for some given initial state, you've chosen sort of some given number of electric charge clusters that you can create. But where you now conserve that net charge pattern, that gives you the exponential fracturing, because there's sort of all these different permutations that you can have of the charge pattern. And then once you have chosen your initial state to reside within one of these Krylov segments, you're never going to evolve to a different one. Okay, so this is a nice physical significance for this Hilbert space fragmentation. And what we observe experimentally, okay, here's just a cartoon first to illustrate, is that when you track actually the center of masses of these electric charge clusters, you'll find that the spatial distribution is statistically localized. Okay, so that's actually what we track. And we do this sort of with a uniform measure over all the states, so it's the infinite temperature state that we work with. Okay, to check that we do actually have Hilbert space fragmentation in this new Hamiltonian, the V1 model that I talked about, we also look for sort of state-dependent dynamics to begin with. And one thing that we observe, for instance, is that you can get state-dependent localization. So here you see that you have some initial state, and then you let it evolve over time. It doesn't really change. A lot of things are frozen. And that's not always the case if you start from a different initial state. And so the way you can think of this is that the state-dependent localization comes where you've saturated the number of charge clusters, but you've also left no room for those charge clusters to grow and shrink. And then that gives you this localization. And to check that this kind of state-dependent dynamics is actually attributed to the Hilbert space fragmentation, we can actually quench initial states that belong to two different Krylov fragments. Okay, and then we can measure actually what's the microstate projections onto other microstates within the same Krylov fragment versus those in a different Krylov fragment. And we're going to see that those projections within the same fragment, they're all significant, and they're much, much larger than some of the projections onto a different Krylov fragment. Okay, so this kind of a step-like function over here tells us that a lot of this ergodicity breaking that we're observing is due to actually this disjointness of the different Krylov subspaces. Okay, but so far, this is just state-dependent phenomena. There's no clear signature that there's strong fragmentation in this new model that we've worked with. And so in this case, to demonstrate signatures of this strong fragmentation, we actually need to measure these statistically localized integrals of motion, or S-Leoms that we describe over here. Okay, so the OI case, those basically refer to the center of mass projector of a case electric charge cluster. Okay, these are very non-local operators. And then there's a prefactor, -1 to the power of 2i, which just tells us whether or not that particular case charge cluster is charged or is neutral. So again, where I said that your dynamics of the charge clusters are such that you conserve the pattern, right, the net charge pattern, then you can see now that where these QKs, they will label the different Krylov subspaces, right? So for instance, for this example that I show over here, this is charge neutral, so it's -1, QK equals to -1, +1, +1, +1. And so where I started in, okay, I guess I didn't write that here, -1, +1, +1, +1, I'm not going to evolve to anywhere else. Okay, how do we actually extract these QKs? The good news is that even though those observables are very non-local, they are diagonal in the Z basis, so we can actually extract them from sort of the Z bit string snapshots. But now, the challenge is not really actually extracting them from the Z bit string snapshots. The nice thing about working with Rydberg atom arrays, you have single site resolution, you can observe everything. The main challenge that we encounter here in observing the statistical localization is that how do you actually probe the dynamics of typical quantum states, right? Suppose you start from a few different handful of initial states. How do you actually prove that those are the typical quantum states that you're looking at? Well, the only way is really to be able to sample from all the quantum states that you can get, right? So all the Krylov subspaces and so on, and that's not a trivial thing to do. For this, we actually draw inspiration also from the work that Daniel Ma was talking about with sample states from sort of this temporal ensemble. For experiment, we work with sort of a 5 charge cluster symmetry sector. And so let's pick one Krylov fragment to begin with, right? We can initialize some state in belonging to that Krylov fragment. And then we're actually going to make different Z projection measurements at different times. And in doing so, create this temporal ensemble. And then within that Krylov fragment, we're able to reconstruct these S-Leoms, and we can see that, okay, there's already some sort of sub-extensive behavior that's going on. But now we have to actually reconstruct this for all the states within the symmetry sector. And so we repeat this actually for all the different Krylov fragments within that symmetry sector. And then here, to ensure that we have a uniform measure over the entire symmetry sector, we weight this average by the size of the Krylov fragment. And now you have the experimentally reconstructed S-Leoms for actually all the states within that symmetry sector. Okay, you might look at this and you might say, well, you do see this sub-extensive behavior. Is it really because you have a small system size? Does it really persist when you consider a larger fraction or the full Hilbert space? For this, we had to turn to theory where we numerically simulated now what the widths of these S-Leoms actually look like in this infinite temperature distribution. And you can see that there's a difference between those S-Leoms that belong to the bulk, right? Those are sort of partially localized, if you like. The normalized widths go as n to the minus 1/2. Whereas actually for the edges, right, those boundary S-Leoms, those are very strongly or completely localized, right? Those widths are independent of the size of your system that you have. So that's actually very interesting. Okay, so to conclude, we've now really demonstrated two different pieces of work that's sort of subtle forms of thermalization and subtle forms of localization. And the localization, I think, is really quite interesting because it's something that you get even though you've got non-local conserved quantities that's going on. And as an outlook, although I had mentioned a lot of this work in the context of quantum simulation, we also want to come back again to how you can leverage this for doing quantum control. And finally, of course, these constrained lattice gauge theory dynamics that we talk about could be quite interesting to pursue in both the high energy and the low energy sector. And with this, I want to thank actually the students who worked extremely hard on this. So a lot of this work was actually done in Singapore. I only moved to Duke about 1 year and 3 months ago. And the work was really led by Lu Heng, who is a graduate student. Here he is as a postdoc in my team at Duke. And a very, very talented undergraduate student at the time, Raj, who is now a graduate student at Stanford. And of course, thanks to our wonderful collaborators, Wenwei and Natalie. And thank you.
All right, thank you, Huanqian. Someone, please.
Thank you for amazing talk, super cool. So regarding reconstruction of the statistical local integrals of motions, by the way, I don't know where this question is valid or not. Like, have you found all such local integrals of motions or subset that you can compute?
So let me try, so you're asking about within this model, or are you asking about?
Within this model.
Within this model, okay.
Have you found all integrals of motions or a few, like whatever that allows analytic expressions?
I don't know if we have a proof for showing that we have found all the localized integrals of motion.
I just thought it would be super cool if you use machine learning to figure out all integrals of motions, and if you can find something more than what you expected, that would be cool. If you recover everything, that would be also super cool.
I totally agree. Thanks very much for that suggestion. Yeah.
Thanks for the nice result. I think, well, in one case, at least in the TAC, you can prove they are complete. They are generated instead of the commutant.
Okay.
I don't know here, but in that case, there's a proof.
Okay, thank you.
I think in the paper by Huanqian Loh and Lessig. Thank you. It was really nice results. It was kind of two things. Two things. Can you compute measure bounds? Now you have access to a lot of things in this calculation. So with these lines, you can prove a bunch of stuff. Would you mind even to compute two-point correlation functions at different times and look at the saturation values? And also, second question, there are suggestions for systems with quantum fragmentation where now you would have some coherencies, which go pretty much in the line of quantum error codes and these ideas. Have you thought about that?
Okay, so the two-point correlators, thanks for bringing that up. I think that's something that we would like to look into. We haven't done that exactly. And then for the quantum error correction, that's something that's very new to me, and I would love to learn more about that.
It was beautiful results.
Yeah, okay, we can chat.
Thanks for the wonderful talk. So I just want to ask a follow-up question following the Suman's question. So what's the like order of magnitude or the exact number for the local integrals of motion? Because like for MBL, the number for Lam is almost of the same order of magnitude, like the degree of freedom in the system. So what, is it like ON or exponentially many such local integral of motion? What's the order of magnitude for that?
It's exponentially many, because if you think about it, each localized integral of motions or each set of them sort of denotes one Krylov subspace, and that the number of the Krylov subspace has to go exponentially with the number, the size of the system.
Okay, so it's really like in the statistical meaning, there are some many-body localization that you have shown, like in Krylov space. Can I understand?
That is our understanding, that it is statistically localized. It is a statistical form of many-body localization.
Okay.
Hi. Yeah, thank you for this beautiful work. I have a question. I'm kind of really want to learn more about the statistical localization. Would you mind go to the slide that you show the measurement and the key result? Maybe, yeah, this one. I try to understand the plot on the left better. It's like they do this like, how to say, phi 1, phi 2 are done it at a different experiment cycle. Is that correct?
Mm-hmm. Yes, that's right. We initialize them in different experiment cycles. Yes.
I see. So for the state initialization, how you enter a specific sector during the initialization stage?
Oh, okay. So so for the different Krylov sectors, we know what initial states belong to that Krylov sector, and then we pick one. Although you can check this with more than one, and we simply just use the usual tools that we have. We send in certain lasers that are tuned that tune certain sites off resonance.
Oh, so you kind of have individual addressing.
Yes, that's right. Individual addressing. Yeah. So just the usual toolbox.
I see. Okay. Thanks.
Okay.
Yeah, thank you for a nice talk. You showed results about different models like QPX, PQ, and so on. And so it looks like you can engineer many different constraints. So where is the limit there? Do you ever have to worry about, say, noise in the motional degrees of freedom and so on?
Yeah, great question. Thanks, Federica. So we are limited a little bit by how many of these atoms we can squeeze within a blockade radius. So we had stopped at PPX, PPQ, for instance, because when you go beyond that, then you need to go to even higher Rydberg levels, which then becomes very tricky to work with, so that your blockade radius can be larger, and so on. So there were technical constraints, but in terms of actually now combining the different Qs and Ps, actually I think there's quite a lot of room that you can do over there, right? Because we not only have just QPXPQ, PPXPQ, and so on, but you can have different combinations and different weights of them. And so actually I think there are many, many possibilities that you can now explore. Yeah.
Yeah, I had a related question to Federica, which is my impression is that a lot of Rydberg experiments don't like to work in this like anti-blockaded regime and so on, because it's a lot more sensitive to like positional disorder than like standard Rydberg blockade. So is your system just better at this, or is it like not that severe in general?
Thanks for the question. So you're absolutely right. It is trickier to work with Rydberg anti-blockade. And actually, when we first saw some of this, when we first tried to look for some of this initial data, say with the QXQ model and the Z2 scarring, we didn't actually see that. And that's because our system just had too much position disorder, right? It's very sensitive to position. Once you're off, then that goes a factor of 6 in terms of your van der Waals interaction strength. So we had to cool down the atoms. And it wasn't that bad, actually, once you cooled it down to get the position disorder more under control.
About the statistical localized, in principle, there are 8 of them, system size, minimum system size, and then like you can evaluate the typical differential sectors, but with only 8 of them, you can generate all the set of concept factors. So the number of these QKs.
Okay. Yeah, I think I totally misspoke. Yeah, it is the. Yes, thank you. Yeah, thank you. Yes, it's the set of them that actually is exponentially large, but the QK itself actually should be linear. Yes. Yes, that's right. Yeah. Thank you for pointing that out.
Any more questions? If not, then let's thank Huanqian for this very lovely talk. Thank you. And then we'll break for lunch. We'll start again at 2 p.m.